In this video, we're going to explore the probability of mutually exclusive events and also non-mutually exclusive events. And what I'd like to do is just to dive straight in with an example, and we'll compare and contrast how mutually exclusive and non-mutually exclusive are different from each other. So I'm going to begin with the example that is in your note. Haley is a fastball pitcher. She likes to feature, she's featured in the student versus teacher baseball game. She's in the bottom of the ninth, 2 outs, bases loaded, tie game, and guess who's up? Yours truly. She's tempted to hit me with a pitch, but she decides that maybe that would, first of all, score a run to lose the game because the bases are loaded. But then, secondly, there might be some other consequences, haha. So she has 4 key pitches that she uses as a fastball pitcher. She has a fastball, a slider, a curveball, and a changeup. She tends to go to her curveball 1/3 of the time, her slider half of the time of the curveball, changeup 1 in 10 times, and her fastball the rest of the time. I feel like I have a pretty good chance of making a base hit or better if she throws a fastball or a slider. Those are the 2 pitches that I prefer. So let's do some math, and first of all begin with what is the probability of her throwing any one of these 4 pitches over the plate. So the probability of the curveball is 1/3, which we can write as a fraction, and best to leave it that way so it's not a repeating decimal. The probability of the slider is half of the probability of the curveball, or a half times 1/3, which would be 1/6 of the time. The probability of the changeup is 1 in 10, and the probability of the fastball is what's left over. So let's figure this out indirectly. Let's do 1 minus 1/3 minus 1/6 minus 1/10. Now to subtract the fractions, we need a common denominator so that the portions are all the same size. If I count by 3s, count by 6s, count by 10s, the first number I get to where all of them match is 30s, or 30ths. So we can start off with 30 30ths, and we will subtract the proportionate number of 30ths from each of these pitches. So to go from 1/3 to 30ths, I have to multiply by 10. To go from 6 to 30ths, I multiply by 5, top and bottom. And to go from 10ths to 30ths, I multiply top and bottom by 3. So I end up with the remainder of her pitches being 12 out of 30 times. However, that can also be reduced to lowest terms, which would put it at 2/5 of the time. All right, so 1/3 again here, 1/6, 1/10, and 2/5 for each of those respective pitches. So what is the probability that I will get a pitch I don't want? So let's remember that the ones I don't want are the changeup and the curveball. So the probability of getting a curveball or a changeup, and I've used CB and CU just because they both begin with C. So there's no multiplication here, it's just an acronym for each type of pitch. Okay, so that'll be the sum of those 2 probabilities. So I have 1/3 plus 1/10. Again, I can't add these together unless they're the same size. We can convert them into 30ths, in which case I will have 10 30ths for the first pitch, 3 30ths for the second pitch, end up with a probability of 13 30ths, or less than half the time. Now, how could I use this to figure out how often I will get a pitch? Well, there's 2 different ways that I can do it. Okay, in part B of your note, we're going to use an indirect method. And in part C, we'll use a direct method. So indirectly would be taking all the pitches that she throws, or having the probability of the ones that I like being subtracted from 1. Or having the ones I don't like, subtracted from 1. So we just figured those up here above. So we have 1 minus 13 out of 30, which is the same as 30 over 30 minus 13 over 30, or 17 out of 30. So there's a probability I'm going to get a pitch I like more than half the time, because half the time would be 15 out of 30. Now directly, I could have just gone up and used the probabilities for the ones that I do like. So let's put those in. So the probability of like, or getting a pitch I like, could be a third plus a tenth. And then this is going to start to look a little bit familiar. Oh, I missed one. Hang on. The ones I like are, sorry, the slider, which is 1/6, so that's where it is. Thanks for your patience. Sorry, these are the ones that I do like. I should have put an X here for the ones I didn't like. I put a check mark. That's what messed me up. There we go. Okay, let's try that again. My bad. So the ones I like are in red. Okay, so I've got 1/6 plus 2/5. I can convert both of those into a common denominator of 30ths, as we did up here. And we can extract those values in a similar way. So in order to get to 30ths, I have to multiply top and bottom by 5. In order to get to 30ths from fifths, to multiply top and bottom by 6, and I get 17 out of 30. So not surprisingly, these two answers are identical, whether you use an indirect method or a direct method. Okay. So what do the answers in this question tell you about the probabilities of events that can't happen at the same time? And the reason these can't happen at the same time is because quite clearly she can't throw two types of pitches at the same time. So when you have events that have nothing to do with each other happening, or that can't happen simultaneously, we can add them together to get the overall probability. Okay. So just to put this idea of mutually exclusive in a visual format, I'd like to introduce Venn diagrams. So if we let the first event in a series of two mutually exclusive events be event A, here it is, and we have event B, they can't happen at the same time, but we want to know the overall probability of both of them happening, we can just add their probabilities together. And notice the use of the word or here happening. Let's look at a couple more examples. Let's say you roll 2 die, and what is the probability of getting an 8 or a 12? And we've drawn that summation dice diagram many times, probably to the point where you can do it even quicker than I can right now. I'm going to highlight the areas where we would have a sum of 8. So I would have a sum of 8 here at 4, 4, and I do happen to know that there's also an 8 in that diagram in 4 more locations for a total of 5. So the probability of rolling an 8 is 5 times out of 36, which is the entire 6 by 6 grid. What is the probability of getting a 12? Well, you'll remember that the sum of getting a 12 only has one occurrence. It's down here in the bottom right corner. So if we want to know the probability of getting an 8 or a 12, and note that we could write it like this as well. Okay, either way, we would simply add those two probabilities together. In this case, we would get 6 out of 36, and reducing it to the lowest terms would be a 1/6 probability. All right, let's switch from dice to decks of cards. Let's say that you're going to draw from a deck of cards, and you want to know what your probability is of getting a 5 or a 7. So what's your probability of getting a 5? Well, how many 5s are in the deck? There are 4 of them out of a possible 52 cards in an entire deck. What's your probability of getting a 7? Well, similarly, there are also 4 7s in that deck as well. So if you want to know the probability of getting a 5 or a 7, you can add those two things together because you can't draw a 5 and a 7 at the same time. We would get 8 50-seconds. We can reduce these both down. They're both divisible by 2, but they're actually even bigger than that. They're both divisible by 4. And if you divide top and bottom by 4, you will get a 2/13th probability for those events in an OR scenario occurring. Now what happens if you continue with this deck of cards, but let's say you want to have a face card or a black 4? Well, what's the probability of getting a face card? And I'm going to go straight, if it's okay with you, to here. We'll do this thinking as we progress across the page. And I'm just going to give myself a little short form note of face card or a black 4. So how many face cards are in the deck? Well, let's remember face cards are your jacks, your queens, and your kings. And there's 3 of each of those. So there's 4 of each of those. So 4 of each of those 3 types means there's a 12 50-second probability of drawing a face card. Now I can't draw a black 4 at the same time as drawing a face card, so what's the opportunity for a black 4? Well, there are 4 4s in a deck, but only 2 of them are black. So we have a 2 out of 50-second chance, which means we have a 14 50-second chance overall of getting a face card or a black 4. Both of these are even numbers. I could divide by 2, and I know that I get a prime number on top, so that's the greatest common factor. And when I divide 52 by 2, I get 26. Now, let's go back to this example right here, and let's modify it just a wee little bit. What's the probability of drawing a face card or a spade? Now, this is an event where it's possible to get a card that is a face card and a spade. You could end up with the jack of spades, you could end up with the queen of spades, you could end up with the king of spades. So there are some items in this deck that have both attributes. How can we handle that? Well, maybe we can visualize this in a different way before we mathematically answer that question. We could draw a Venn diagram that shows all of the face cards and that shows all of the spades, and seeing where those overlaps are. So we already said there are 3 cards that are going to overlap and have both criteria. How many spades are there all together in a deck? Well, there are 13. So if I subtract those 3, that means there are 10 that are in this section of the Venn diagram because they're spades only. There are 12 face cards altogether, but if I take away those 3, I'm left with 9 here. Okay? So that's one way we can envision it. We can also remember that we learned about an equation back in our combinations unit that looks something like this. The probability of a face card or a spade where they have some overlapping qualities is equal to the number of items in this circle plus the number of items in this circle, but then we have to take away the overlap because we don't want those to count twice, we only want them to count once. So we have the probability of a face card plus the probability of spade minus, I'm just going to erase this here, the probability of where the face cards and the spades intersect. Okay, so again, there were 12 altogether for face cards. There were 13 altogether for spades. We're going to subtract the 3 that they have in common. Now all of these are out of 52, and I could draw out of 52 3 times, or mathematically I can do this and it means the same thing. So I end up with 22 out of 52, which can be reduced down to 11 out of 26. Notice that I could get this 22 another way as well. I could get it by adding up the areas of the Venn diagram. I could also do 9 plus 3 plus 10 and still put them all out of 52 to get 22 out of 52. So two ways. Big circle plus big circle minus the overlap, one of the overlaps because it would be counted there twice, or find out the number of items that are in each area of the Venn diagram and add them all up. Okay. This scenario here, where we have the overlap of some items or two events can, quote, happen simultaneously, is called non-mutually exclusive. So non-mutually exclusive means that we have event A and event B, but they're not completely separate. They do have some outcomes in common with each other, okay? And there you go. Let's do one more example where we take this Venn diagram up to a three-circle Venn diagram and look at some probabilities from it. So the example that's in your notes involves looking at the marketing department for a magazine company, okay? And all of the values that go into the Venn diagram are given there. How about we begin in example 4 by putting that Venn diagram together. So, we're going to begin, and let's draw this Venn diagram large enough that you're able to give it the detail it deserves. Okay, and it doesn't matter to me if you draw perfect circles or not, because mine are most certainly not perfect. The three magazines that are featured in this particular question are Teen World, I'm going to call it TW for short, Star Watch, which I'm going to call SW, and Fashions, which I'm going to call F down here. Now, it says here that there are 25 that subscribe to Teen World only. So that would mean that in this section right here of the Venn diagram, we can put 25. You don't have to worry about some subtractions. This is a kind question. It says 19 subscribe to Star Watch only. So that's looking at this section over here of the Venn diagram. We can put a 19 in. And in similar fashion, we're told that there are 15 for Fashions magazine. Okay. We're also told that 11 subscribers get all three magazines. So we can put those dead center to overlap for the three. We are also told that there are 41 that subscribe to Teen World and Star Watch. So that means that 41 of them subscribe to here, that whole region. So if we only want to know what goes in here, 11 of them are already accounted for in this region of the red eye. We're going to have to take those 11 away to get the rest that go just in this section here, which will be 30. We're also told that 28 subscribe to Star Watch and Fashions. So again, that 28 is for the entire, I like just calling it the cat's eye, this whole overlap between the Star Watch and Fashions circles. So if we want to know what's in this little section, we have to do 28 minus 11, which puts us 17. And then finally, we're told that there's 32 for this entire section. So if we want to know what goes in just this piece, we have to do 32 minus 11, or 21. Okay. To finish off our Venn diagram, we would also put a box around it. You can use a straight edge, easier than I can on the whiteboard. And we would ask, are there any members outside of the set? And the answer is no, they're all accounted for. In the diagram, if there were some that were outside the set, we'd put them here. If you want the total number of things in the set, you can put it up here. We might need that. Okay, let's check it out. So now in part B, we have a whole bunch of probabilities to explore. First of all, what's the probability that a randomly selected subscriber in this particular diagram subscribes to all 3 subscriptions? So the probability of all 3 is equal to 11 out of the total possibilities. So we are going to need to add all these up to see what the total number of items in this set is. You can pause the video and do it, or you can believe me when I say that there's 138. So 11 out of 138 would be the probability. 11 is a prime number, so our answer can stop there. All right, and number 2, what's the probability that someone has exactly 2 subscriptions? So where in the Venn diagram do we find those pieces? Well, exactly 2 would be this little part up here, this little part in here, and this little part in here. It would not include the 11 because they have all 3. So we're going to add those 3 together. We have 30 plus 117 plus 21 out of, and the probability is still out of the total of all subscribers, so we're still out of 138. That comes to 68 out of 138, which 2 even numbers, so we know it can be reduced. When you divide by 2, you get 34 out of 69, and that's as low as the probability can be expressed as a fraction. Let's look at part 3 in your note, which says what's the probability that there are at least 2 subscriptions that random subscribers belong to. So at least 2 would include these areas, but would also include the middle, because that's 3, so it's more. So it'd be 30 plus 17 plus 21 plus 11, all divided by 138, because again, it's still out of the total. Okay. When you add all those up, you get 79 out of 138, and there are no common multiples between those 2 numbers, so it is expressed, therefore, in lowest terms. Part 4 of your question says, what is the probability that a randomly selected subscriber receives fashions? So fashions is this area right here. It's this circle. So we have to include all of the subscribers that are in there. So the probability for Fashions magazine is equal to 21, 11, 17, and 15 altogether. Still out of our total for the entire Venn diagram, which is 138. This comes out to 64 out of 138. Again, both even numbers. It can be reduced down to 32 out of 69. And again, no greatest common factors. That's in lowest terms. The last part of this question asks us, and I'll put it up here, to determine the probability that a randomly selected subscriber receives Star Watch or Teen World. So Star Watch or Teen World. Now notice there's some overlap in there as well. Okay, so we have a couple of ways that we can do this one. We can add up the areas and do it out of the total, or we could also realize we could do it a little bit indirectly. All of this area here includes the 138 except for these 15. I think that's the easiest way to do it. But let's try a couple ways to show that there's multiple approaches you could take. So, Star Watch in union with Teen Watch could be everybody minus Fashion World, which is just, or Fashion World only, which is 15 out of 138. And that comes out to 123 out of 138. And like I said, in a similar fashion, you could also just add these guys up, right? You could do 25 plus 19 plus these guys in here. I'm going to put them together and make 41 if you're okay with that, plus 21 and 17. And you can make that out of 138, and it'll add up to the exact same thing. Okay. Depending on the question, if you did not know these individual numbers, but you knew the values for the entire circle, you could use like we did in the previous example, and you could do the probability for Teen World plus the probability for Star Watch minus where they intersect, which we know is 41, okay, out of your total. So there you go, a whole bunch of different ways of looking at mutually exclusive and also non-mutually exclusive events. If you have any questions with the practice, please let me know.